Hi everyone, my name is Santosh. Today I want to present about assignment 2, SSCP2613, which is about the differential equation. So I want to introduce our lecturer, which is Dr. Rosenda within China. And then this is our group member. So we have Yap Ziyang, Yi Jiajun, Gregory Hong Xiao Zhao, and Chen Jiaseng. Next, we go to our task today, which is MVS to then equation using second order different ODE. So the top one is then oscillation, while the bottom one is the then oscillation. And then this is the assumption we use in our calculation. So we have mass per well equals to 300 kg, spring length is 250 millimeter, and spring constant is about 19,620 Newton per meter, and the compression of spring is about 15 cm.
Hi everyone. Today I want to talk about undamped oscillation. So at the top you will see the fundamental equation for the undamped oscillation. So is my prime plus ky equal to 0. This mathematical model describes a system like a mass on a spring that oscillates forever without any friction slowing it down. The general solution for this equation is given by yt equal to a cos omega t minus phi. This tells us the position y at any time t. The a is the amplitude, is about the maximum displacement. The omega is the natural frequency, so that how fast it oscillates, and the phi is the phase shift, it's starting the position in the cycle. So for our specific problem, we have the initial conditions, which is the object starts at the position of 4 cm and has an initial velocity of 40 cm per second. For this part, this slide is show the mathematical derivation. So we will not go into every detail, but the main takeaway here is to show that the cosine from the solution we are using a mathematically sound and equivalent to other forms. It's essentially proof that we can confidently use the a cos omega t minus phi formula to find our answer, which is very convenient for understanding the physical properties like amplitude and phases. So with this theory in mind, just apply it. For this substitute value part, first we need to determine the angular frequency, which is calculated to be 8.0x7 radians per second. This value depends on the mass and the spring constant, which were used to get this result. Then, using our initial position 4 cm and the initial velocity 40 cm per second, we solve for the amplitude and phase shift. The calculation, so our amplitude A is 6.361 cm. This is the furthest the object will move from its center position. The phase shift is 0.891 radians. Putting it all together, we will get the final equation that precisely describes this specific oscillation, which is yt equal to 6.361 cos 8.0x7t minus 0.891. For this graph part, this is a plot of our equation. The vertical axis of the position and the horizontal axis is time. You can see the smooth repeating wave patterns. The peaks of this wave are at positive 6.361 cm and the troughs are at negative 6.361 cm, which is the amplitude we just calculated. This visual conforms our solution and gives us a clear picture of the object oscillating back and forth in simple harmonic motion.
So for then oscillation, we have to use this equation ny prime prime plus dy prime plus ky equals to 0, which is the second order ODE for an oscillation. And then for we have three type oscillation. So for our then we can get two different roots. And then for critical then we can get the same root. Well for under them we will get an compressed roots.
Now let's move to the situation of damped oscillation. We assume there's a vertical displacement y, a spring constant k greater than 0, a body mass m greater than 0, and a damping constant d greater or equal to 0. It's described by the solution of m y double prime plus dy prime plus ky is equal to 0. So the roots to the second order differential equation above is r equals to negative damping coefficient plus minus the square root of damping coefficient square minus the circular frequency square. So a system with damping coefficient smaller than circular frequency is called underdamped with general solution at what I have drawn underline over there. And beta is equal to square root the damping coefficient square minus the circular frequency square. So plug in all k, the k and the m value, will get the circular frequency is equal to 8.087. Right now, we assume that the damping constant is equal to 200 and m is equal to 300. And we assume that when time is equal to 0, the position of the spring is at 5 meter, and we assume that it's not moved, so 0 velocity. So from the second order differential equation above, we'll get the roots is equal to negative 0.383 plus minus 8.080i, which I've drawn and underlined. We plug in all the values into the general solution, we'll get AE power negative 0.333t cos 8.080t minus phi. We differentiate that, we'll get negative 0.333 AE power negative 0.333t cos 8.080t minus phi minus 8.080 AE negative power negative 0.333t sine 8.080 minus phi. And from the assumption at start, if we plug in the time is equal to 0, the original equation will become 5 equals to a cos phi. And another a cos phi, right. And we also plug in the time equal to 0 in our differential condition, we'll get 0 equals to negative 0.333a cos phi plus 8.080a phi. So we need to find phi now. At the end, we will find phi is equal to 0.041 radian. So we plug into the equation earlier, we'll get A is equal to amplitude is equal to 5.004. So the equation for the damp oscillation is 5.004 e power negative 0.33 t cos 8.080 t minus 0.041. As you can see, the graph is at the left side. The graph oscillate the amplitude is big at first, but slowly as time goes, the amplitude becomes small and eventually becomes zero.
Okay, so now we look at the critical dam. For critical dam, we're using the similar ways. We're finding the omega naught and then assume d equal to 2 omega naught. After that, we solve the differential equation m y prime prime plus d y prime plus k y equal to 0. We will get r. R is equal to negative 8.087. Then we put inside the differential equation yt and also y prime t to get a equal to 5 and d equal to 40.435. So here is the graph after we get the differential equations and we substitute for a and b. Then by using the decimals, we plot a graph of critical damping. This will show like a curve at the middle and then go until approach to 0 here. So this is critical damping.
Okay, so for over there, we need to ensure our D is very large so that D over 2M is very large compared to the omega naught. And then so by substitute the value, we will get the equation and we will get the root, which is negative 1666.67 minus 1666.647. So for R1 we'll get negative 0.02, while R2 is negative 3,333.314. So we'll get YT equals to A E power negative 0.02T plus BE power negative 3,333.314T. So by substituting value, we'll get A equal to 5 and B equal to 30 times 10 power negative 5. And then, so this is our graph for overdamping, which is, we will see that there's no oscillation for the graph, and so that's why we use our D is very, very large value. If you use small value, it seems like the graph looks like the critical damping. And then this is our reference to use in our assignment, and that's all for our presentation. Thank you.